In this video, we're going to discuss instantaneous rate of change. So what we would really like to compute is a change at any given point. Average rate of change is computed between 2 points at some distance apart, as we discussed in the last video. We need to pick an interval of a certain length to then actually compute the average over. And if we pick shorter and shorter intervals, we will get closer and closer to the point and therefore be able to describe the function behavior really close to the point of interest. Let's make a fast sketch of what that might actually look like. So let's say I have a graph of some function. Okay, so let's say here's my function. I don't need a formula for it, purely graphical observations. And let's say this is my point x. And this is the point at which I am interested to construct or to compute an instantaneous rate of change. So for example, like in the Leaning Tower of Pisa example, I wanted to compute the velocity at 3 seconds. So if I want to compute an average at that point, what is it that I can do? Well, I can of course find a point somewhere else on my graph and compute the average between these 2 points. Okay, but now those 2 points are pretty far apart. I can probably do better. I can find a point closer to my point of interest and then compute an average through these 2 points. And clearly, the closer points, the second point that I pick to the first one, the better my average will describe what actually happens at point x, right? So the closer I move, it's going to get harder and harder to draw lines. These guys are what we've been calling secant lines. And if I move so close, if I essentially move my second point to be on top of my first one, also right here, and draw the line through those 2 points, what I will end up with is what we call a tangent line. The names actually come from Greek. Secant means to cross. So you can see here that all of these red lines cross my original function. Where tangent, the word tangent means to touch. And you can see that my blue line here only touches my purple function. Okay, let's take a look at how this works in animation. So let's say the purple point here is my point of interest, and the green one is the point that I'm computing the average in between the purple point and the green one. And if I take this green point, so far I have a secant line, it crosses my red parabola. But if I move my green point closer and closer to the purple point, see how the secant line changes and actually becomes a better approximation of what happens to the function. The green line now looks a lot more like my red parabola than it did here. Here the green line is kind of far away from a parabola, it doesn't quite match its shape. But the closer I get, the more my line mimics the shape of my parabola. Unless I get right on top of that point where I get just one line and therefore I'm able to actually think of the tangent line here. Okay, thinking also back to our previous example of the COVID-19 curve, we see the exact same logic here. When we were taking, what was it, 1 month, right? So March 24th, when we were taking averages over a month, this secant line doesn't quite describe the curve very well. But if I were to take an average between 2 points that are closer together, then the line connecting them will mimic the shape of my function much better. If then we think about what the last question that part asked, when a case is growing fastest, it means I'm actually after a particular day at which I can draw my secant, or rather my tangent line, and it's going to be the steepest of them all, right? So now I can start thinking in terms of tangent lines, so particular points and just the tangent to the curve. Okay, let's discuss this in a little more generality, going back to my previous sketch. So here is a graph of a general function, and the idea was I would like to compute the instantaneous rate of change at this point x. And the way I'm going to do it is I'm going to construct the secant line through the second point, and then I'm going to keep moving the second point closer and closer to my first point until they essentially are on top of each other and my line becomes a tangent line. Okay, so let's think about how we're going to do that here. I have these 2 points, and of course I can describe them as x and let's say x1 or x2, but because I'm going to be moving this point closer and closer to the first one, it makes sense to describe them as x and the second point as some distance away from x, because it's this distance that I'm going to be shrinking. Okay, so let's say that this distance, we will call it little h, and then the coordinate of this point is x plus h. Okay, so let me label this here. Okay, and now the slope of the secant line is just the rise over run. As usual, we're just computing a slope of a line between 2 points. So now I just have to find what is the rise between these 2 points and what is the run. Okay, so we're going to need to label a few more things on the graph. This is my function f of x. So if this is x, then this, the y coordinate of this point, corresponds to f of x. Right, I can connect them like this so we see this better. And if this is my point x plus h, then the y coordinate of this point is going to be f of x plus h. Be careful of a function notation here. X plus h goes all inside the function f here. Okay, so now my rise, how much have I risen between this point and this point? I've risen this much. So I've risen this much. And therefore I've risen the difference between this whole height minus this little height. Okay? Pause here for a second to persuade yourself that that is in fact the case. That the distance that I have risen is the difference between f of x plus h, the larger of the 2 heights, minus the littler one. Okay? Once you've persuaded yourself, we can write this down. So the rise is f of x plus h minus f of x. It's the change in y. Divided by the run. So how much have I run from here to here? Well, I've run this much, or h. You can also think of that as x plus h minus x, but it's going to be the same as just h. Okay, excellent. This is the slope of a secant line, right? A line through 2 different points. Another way of saying is this is the average rate of change between the 2 points, x and x plus h. Okay? So this guy, let's label this too, this is the average rate of change. To get to the instantaneous rate of change, I need to move these 2 points closer together until they're essentially on top of each other. So what I'm going to do next is to compute the slope of the tangent line. And this is essentially exactly the same, except for now what I would like to think of is I would like to move this point closer and closer to my original point at which I'm interested in the instantaneous rate of change. But that just means that I'm moving this x plus h closer and closer to x, which just means that I want the distance between these 2 points to essentially not be there or be 0. So the slope of the tangent line is the same as the slope of secant line as h goes to 0. Okay? I would like to make h as little as possible, essentially 0, and that will be the slope of my tangent line. Okay? So the way that we write that down, h going to 0, isn't really a concept, isn't really a number we can plug in, particularly here, because look, this is the slope of my secant line. I cannot easily plug in h equals to 0 because then I'll be dividing by 0. So the way that we rewrite this h equals to 0 is going to be in terms of limits. I will take a limit as h goes to 0, and we're going to spend an entirety of the next chapter discussing what limits really are. And I need to take that slope of the secant line within this limit. So the slope of the secant line, but this is something that I've already derived here. So this just goes here, okay? So it's the limit of f of x plus h minus f of x all over h. This is the slope of a tangent line. We don't know how to compute limits yet, and we're going to learn very soon. But for now, this quantity has a bunch of different interpretations that are all extremely useful. So first of all, the slope of a secant line is the average rate of change. The slope of a tangent line is instantaneous rate of change. Because now we're really discussing what's happening at one point, because the distance between the 2 points have been shrunk to nothing. This is also, of course, the slope of the tangent line, because that's how we computed it in the first place. This is also what we call a derivative of the function at that point. So this is the derivative of f of x at point x. And the notation for that is going to be f prime of x, or df by dx, which really just stands for the difference in the f values versus the change in x. Okay? This is it. This is the definition of derivative, and we will literally spend the majority of our course discussing what a derivative is and how it can be used, but this is where it comes from at its bare basics. Okay? Let's take a look at how that can be used, going back to our example of the watermelon being thrown off the Tower of Pisa. So here I've just relabeled my height function as f, just so it matches the definition this one time. Once we are more comfortable applying it, the name of the function should not matter whatsoever. I would like to estimate the watermelon's velocity in 3 seconds, which means that what I'm really after is not the average over 3 seconds, but the instantaneous rate of change in 3 seconds. And the instantaneous rate of change can be described using this formula. Okay, so let's write this down. Instantaneous rate of change, which will give us instantaneous velocity, not average velocity, but actually instantaneous velocity. Now, going back to this previous slide, I had 2 points, x and x plus h, and I needed this h to go to 0. I needed the difference between the 2 points to go to 0. So my point of interest was x. My point of interest here is 3 seconds. So that means that when I'm computing, the 2 points I'm going to be taking are 3 seconds and 3 plus h seconds as h goes to 0. Okay, so my x in this case is 3, because that's the point at which I want to actually compute the instantaneous velocity at. Okay, and so what we're going to do is just rewrite the definition for the instantaneous rate of change from the previous slide. Notice this here. I'm just going to write this as is right now and then change the quantities that we need to change. So f of x plus h minus f of x all over h. Okay? Now, once again, the x, the value at which I'm interested to compute the velocity is 3. So my x will be 3. And my function is this guy right here. So I'll be plugging this function into this expression. Be very careful here. You're going to have to be very, very conscientious of how you use function notation here. And we will do a bunch more examples in class, but you actually really have to mind your brackets. Let me rewrite this one more time, but now with 3 for x, because this is where we're interested in it. So f of 3 over h. And now I actually have to plug my function in. So f of 3 plus h means that I have to replace this x by 3 plus h. So this 3 plus h will go everywhere x was, okay? Everywhere. So it's going to replace this x directly, not be 3 plus h otherwise, but this x will get replaced by 3 plus h. Pause here for a second and try to see if you're going to actually do this correctly, okay? So take a second here and try to plug this in for yourself, okay? So what you should be getting, I'm not changing the limit, this is just something that I'm for now computing with. F of 3x plus h should be 55 minus 4.9, and then 3 plus h replaces the entirety of x. Okay, so this guy is my f of 3 plus h, minus f of 3, which would be 55 minus 4.9 times 3 squared, all divided by h. Okay, and if you're really careful, expand out the brackets, pause the video once again, expand out the brackets, and what you should be getting is the limit. And what do we have? Minus 4.9h minus 4.9 times 6. Okay, I didn't expand it out yet. Okay, so what I have is it's this quantity that is the instantaneous velocity as h goes to 0. As this h goes to 0. Notice that this expression is now much better than the one we started with. In the one we started with, which was back here or back here, h was on the bottom. So I couldn't just plug h equals to 0 in, right? But here, I have no such issue, so I can just plug in h equals to 0. And what this will give us is that this quantity approaches minus 4.9 times 6, which is 29.4, or minus 29.4, and the units were meters per second. Okay, this is it. We've just done our first limit. Nothing too scary about those. The hardest part at this point will actually be making sure that you apply function notation correctly. So I encourage you strongly to practice a little bit with that and maybe review some pre-calculus review package materials to make sure that you're comfortable with the function notation and plugging things in.